Chapter 6. Wave nature of light and electromagnetic waves. Chapter 6.1. Wave nature of light. Let's begin. What's the nature of light? What is light? A stream of tiny particles? Even Newton believed so. Light is wave? Most people nowadays accept that light is kind of wave. But if you ask me, I will say, both are correct. 1. Light, particles, or a wave. Light exhibits both diffraction and interference, so it is a wave for sure. It was verified 200 years ago. A. Diffraction of light. It is not difficult at all to demonstrate diffraction of light. Let's take a look at the following experiment. Experiment 6A. Diffraction of light.
This black plastic film has a very narrow slit. When we view the filament of a ray box lamp through the slit, we see a diffraction pattern. What do you observe from the diffraction pattern? Now, replace the slit with a narrower one. How does the diffraction pattern change? We can produce a clearer diffraction pattern by using a laser pointer. The red laser beam is directed at the single slit. Observe the diffraction pattern formed on the screen. Remember not to direct the laser beam to the eyes. Now, the red laser beam is replaced by a green one. How does the diffraction pattern change?
In the experiment, light spreads out. When it passes a single slit, it is diffraction of light. Different colors of light, due to different wavelengths, spread out differently. For the same slit, red light diffracts the most, while violet light diffracts the least. Light diffracts, but we don't see it often. Why? Because the wavelength of light is very short. You must find an opening small enough to show observable diffraction. 1. Diffraction pattern of light. When light diffracts, light spreads into the shadow of the slit. A diffraction pattern consists of a very bright central maximum and alternate bright and dark fringes on the two sides. 3. Effects of color. We have learned from Ripple-10 experiment that the amount of diffraction depends on the relative size of the opening and the wavelength. Refer to page 60. For the same opening, there is a larger diffraction for longer wavelength, and so we can tell red light has a longer wavelength. 3. Effects of slit width. The size of a single slit also matters. For a narrower slit, its size is relatively smaller. There will be a larger diffraction. To produce diffraction of visible light, the slit must be narrow enough. 1 millimeter? No. 0.1 millimeter? Still too wide. The wavelength of visible light is about 0.5 micrometer. 0.1 millimeter is already 200 lambda. A single slit of about 50 micrometer or even narrower should be used instead. Example 1. Light passing through a gap. To improve contrast of the diffraction pattern, laser source is often used. In part C, the gap becomes even narrower, and so the pattern spreads wider. In other words, there is a larger diffraction. However, as there is less bright energy passes through the gap, the pattern will be dimmer. It may be even harder to be observed. B. Interference of light. Other than diffraction, light also exhibits interference. The simplest interference is the interference by a double slit. Let's take a look of the experiment below.
This is a double slit. It consists of two very narrow slits close together. When we view the bright filament of a ray box lamp through the double slit, we see an interference pattern. What do you observe from the interference pattern? Can you see the dark and bright fringes? Now, try again with another double slit of smaller slit separation. How does the interference pattern change? We can produce a clearer interference pattern by using a laser pointer. The red laser beam is directed at the double slit. Observe the interference pattern formed on the screen. Remember not to direct the laser beam to the eyes. Now, the red laser beam is replaced by a green one. How does the interference pattern change?
Instead of anti-nodal line and nodal line on the surface of water in a ripple tank, we can see bright and dark patches of light on the screen. We call them fringes. In other words, there are evenly spaced, alternate bright and dark fringes formed on the screen. The formation of these fringes is similar to the interference of water waves. Remember that the vibration is greatest for any point on the antinodal line and the least for those on a nodal line. So there is a bright fringe at the end of an antinodal line and a dark fringe at the end of a nodal line. The colors of light and the slit separation will both affect the interference pattern formed. Refer to page 75 of your book. When the slit separation increases, the fringes are closer, and the number of fringes also increases. When the wavelength is longer, such as for red light, the fringes become wider apart. When a light bulb is used, which emits all colors of light, different colors of light produce its own interference pattern, while fringe separation for red light is largest. Hence you will see rainbow colors of fringes as shown. Wave nature of light. Even though Newton tried to insist on his particle theory of light, he failed to explain diffraction and interference using his theory. Wave theory is the only theory that can explain diffraction and interference, and so people accept that light has a wave nature. 2. Ray model or wave model. We may use ray model or wave model in many cases about light. However, for diffraction and interference, we must use wave model in which we have to draw wavefront but not rays. All in all, diffraction and interference are a result of superposition of wave. Do check point 1 below.